Okay, you guys ready? We are finishing lecture, whatever it was from Monday. And then at the end of today too, we'll go over the exam questions and then go over the project stuff as well. So we'll try to keep it short. We'll wrap up the ranking with where we were now. So recap from Monday, we were talking about lateral earth pressures. Hopefully it's kind of self-intuitive, you know, like that soil is going to exhibit a stress vertically due to the self-weight of that soil. But also since it's a granule material, it is also going to want to spread laterally. So also it will produce a lateral stress as well. So lateral meaning like horizontal to the ground surface. So most of the time that's like whatever. We might not need to know that if we're just doing like a consolidation or a shear strength equation. But a lot of times we will have retaining structures where we're going to either have to excavate or potentially put backfill and increase the ground surface elevation for whatever type of construction. So we talked about the two different types, I guess, to recap, there's two kind of theories, one by Rankine, one by Coulomb, and then three behaviors that they both analyzed. So the most common one where they both agreed on was the at-rest condition. And so the at-rest condition is just in situ, nothing's moving, no failure. The horizontal stress is going to, the vertical stress is going to be related to the horizontal stress by this coefficient, the at-rest earth pressure coefficient. And we showed all those equations, the Jacques equation, the Masserech equation, all these equations that relate that to different types of soil properties. But most of the time, these types of analysis are going to be important where there is a potential failure. So this failure wedge occurring. And this is where we have to think and discern between these two types of potential failures. One being an active failure, that's where the soil is moving towards the wall and moving, extending out. And the other one being a passive failure, and that's where the soil is being pushed upon by the wall. So those two examples shown here, and we give examples of where each one of these might be used. But for the real world earth pressure, which is following over the Rankine, usually there's a lot more considered rather than just the soil and the wall. So in this case, we have the potential of a sloped backfill. We have the potential of a sloped wall or like some offset angle of the wall here. And then we also have the consideration of the soil structure interaction. So the granule material of the soil interacting with the rough or the material of the wall itself. So that enters Rankine here, where Rankine developed more so, Coulomb, we went through Coulomb first. Coulomb used all of the different backfills and all these tables and everything. So just to recap too, these equations here for the active and the passive earth pressure coefficients are shown there. But if you don't want to do a bunch of crazy math, engineers already took care of that, and we have those values here. So these values will then be used in the equation to relate to the vertical stress to the horizontal stress. The important thing to remember with that is that it is always in terms of effective stress. So we have these two are different, active and then passive. And then this is the table that shows the general kind of rule with when it comes to some of the typical values of friction factor, which is that delta, the friction angle. Not our normal phi angle. This is just the soil structure interaction. So of it there. So we stopped here on Rankine's theory, this dude, 1850s here. So he assumed a bunch of things to make their life a little bit easier. First one being that the soil is homogeneous and isotropic. You'll see this occur quite a bit. Homogeneous just meaning it's all the same material here, so it's going to have a set density, set friction angle, set cohesion. Also, what he assumed was that the failure surface is a plane, aka it's a straight line. So what we'll see is in slope stability, later on the Norwegian guys and the Swedish guys decided, well, actually it might not, the failure mechanism is not an actual true plane, it's a logarithmic spiral, and they created analysis based off of that instead. But for this, he's just saying it's a straight, it's a straight plane. The other one, ground surface, is a plane as well. So aka it's straight, so or it's, you know, no undulations, there's no, it's just created by a single function. The wall is infinitely long. So this is meaning coming out of paper, out/in of the paper or the screen here. So we're just analyzing a single cross section, and it doesn't necessarily matter the length of it. We're just assuming that it's just it's a plane strain analysis. The wall experiences active conditions or passive conditions, which we'll talk about here in a little bit. It is going to be smooth wall is another assumptions. So this is a frictionless, or that delta function is equal to 0, or that angle is equal to 0. And the biggest one that is helpful because of that 6 is the resultant force. So not stress, well, I guess stress too, but the resultant force is parallel to the ground. So if there is a slope, then it's just going to be parallel to whatever that slope is. Like that. So assumptions are nice, simplifies things a little bit. So in our case now, we have functions here for the active and the passive for that Ka and Kp. So it's, the equation is still looking pretty gnarly, right? But we were able to remove that delta value and simplify it a little bit. Sometimes these are distinguished. You know, sometimes you'll see Kra or Kca, but most of the time it will be stated in the problem like either using Coulomb or Rankine earth pressure coefficients. So just keep that in mind. Those K's values are distinguished between the two, but sometimes they're just showed normally as Ka or Kp. So if we had a level backfill here, then these actually simplify quite a bit. Level backfill, meaning this is equal to 0. So if level, then our Kp is going to equal 1 plus the sine of friction angle over 1 minus the sine of friction angle, which is equal to the tangent squared of 45 plus friction angle over 2. So these are all effective. And then Ka would look very similar, just with these signs swapped. So this is due to like the law of cosines and all that fun stuff that we had to learn in AP classes that engineers already did for us. So we went over these equations already before. Remember, this would be the force, so not necessarily the stress, but this would be that either PA or P. Sorry, I guess this should be a PP there. Oh, yeah, PP. This should be there. And these are always going to be acting parallel to the surface. So in Coulomb's analysis, then there was included a delta value, which was offsetting here. Or is that delta value? Sorry, does not equal 0. Coulomb's does not equal 0. So there was something there. So that's one of the main differences here between these two. So this is Rankine's analysis for a frictional soil only. So frictional soil only. Now what Rankine did was look a little bit further into mixed soils. So still homogeneous, but now what we have is that this material is going to be mixed. So meaning that there is cohesion and there is friction. So it's a typical soil that we usually see where there's a little bit of both in there. So for this, there was an added term here for the cohesion here in the active state. So in the active state, we add this single thing, and this is the stress. So when we correspond this to the force here, then we include it and so on there. So we have that Ka value twice. Now this cohesion, think about what cohesion actually is cohesion allows it to stick together, so hold into each other. So active is the soil particle wanting to move against the wall or travel towards the wall. But now we have this cohesion factor that is actually causing it to bond together. So when we're actually looking at how this affects the stress profile, this could potentially produce a negative value, So just meaning instead of this active scenario, now we have the soil wanting to stay back, and we actually have a tension or a spot where the wall could separate from the soil. So if we have a low enough depth, remember this here is a function of depth, and it increases with depth as we go down. I guess I should say. Erase that. This here increases with depth as we go down. So there's some point, Z, at which, depending on the value of cohesion, where we actually have a neutral plane, a neutral point, where we would technically have tension and then active conditions here as well. Now, most of the time, though, for this active portion up here, most of the time, if it's an active analysis, we know this section down here is most likely going to be the controlling section. So when we were doing this analysis in Rankine, and we are finding the resultant force, then most of the time we will subtract out that negative section, which is what we're doing here. So that's why we're subtracting out that negative section, and we only and we're saying that it only contributes on the bottom section. So, but this is in a, when we're actually talking about designing this, this could be issue because at this point, at this depth Z, we often see like separation of the wall here. So this is where like tension cracks could actually form. And we could have separation from this, even though the majority of the soil is still acting in that active capacity. So if we have tension cracks, this could be very problematic in areas with freeze and thaw, right? Because you're allowing moisture in. And usually if you know this scenario is gonna happen, you would replace that topsoil anyways with some type of aggregate, like an aggregate that would allow water to expand and contract uniformly instead of, allow water to drain out, instead of allowing water to pool back in there and cause an added stress on the top of the wall that may cause bending or failure at the top. So this is only in the active case, because remember, the soil is going to be pushing against or moving into the wall, or actively moving against the wall. So the cohesion, it offsets some of that, essentially, because the cohesion is holding it together. Now for the passive state, though, it has the opposite contribution. Because passive is the wall is going to be pushing on the soil. So this cohesion, this pulling in of the particles itself, is actually adding to that fact. So these are same equation, obviously different coefficients, but obviously the only difference is that addition here now. So if we're looking at the total force being applied, then we would have that added addition there. So we would need to do the same thing where if we were finding the the resultant, then we would have the two combined here for the resultant, and then finding the offset of that there. So essentially in this passive state, which makes sense, the wall is pushing against the soil. So the resistance of the soil means that there's no tension cracks. And full contact. So going back to the active on the previous slide, this Z naught value, that's that depth to that neutral axis. And that is really important in design when we're talking about this with these retaining structures. You can see the influence of that is primarily going to be that cohesion value right there, that cohesion, which is a soil property. And that's from our Moore-Coulomb strength criteria, finding that y-intercept. So the higher that value is, then the deeper that Z value is, because the more the soil is going to want to hold on to itself, and the more tension, or the deeper the tension cracks will be. This is an example where the strength of the soil, the cohesion, is usually a really good thing. Like we would want that thing, or that increases our strength. But in this case, that cohesion actually could potentially have an offset if it's not accounted for in the design or the actual construction of our tension, or of our retaining structure.
So which one would have more force?
Yes, yeah, passive.
What's the difference between, because this is a mixed soil where we're doing a lot of pressure, passive with the wall pushing on the soil?
Yes. No, yeah. So it's the failure of due to the wall like being pushed on by the soil. So when the wall is pushing on the soil, the resistance, the resulting stress is the passive. And so, and when the soil is doing the failing, it's actively failing, then that resisting stress of the soil is in the active state. That makes sense? Okay. So I can think of other ways to, we can talk if it's still not making much sense. But that like passive or active, you're in terms of the soil. So the soil is either actively doing, like failure is still occurring, or movement is still occurring, but you're either that the soil is moving forward towards the failure source or getting pushed on by it. And so the soil has different defensive characteristics than it has offensive characteristics, basically. That's it. All right, let's look at an example here. So anytime you see a retaining wall structure, especially in FE or PE, always look and see and like underline what it's specifically asking for, either Rankine or Coulomb, because the little pictures will look the same, the stuff they give you will look the same, but the analysis and the actual K value would be different. So this one's asking for Rankine, asked to draw the earth pressure diagram behind the wall. With the surcharge there of 800 PSF, and then finding the resulting active force per unit length of wall. So we have two soils, so different stratigraphy here. C is one is a mixed soil here. Soil A is mixed, and then soil B is just cohesionless, so it's a granule material. And then we're given the dimensions. So this one is going to be 110 pounds per cubic foot. And then the other one is going to be okay. And then the other one is going to be 118. So first what we need to find is that since it is active, we need to find the K active, and then for this first layer, and then the K active for this second layer too. So both of them have friction angles. So for the top layer, this K active is going to be 1, well, we'll use the same equation, but 1 minus the friction angle over 1 plus sine friction angle. And so that's 30. So 1 minus sine of 30 over 1 plus sine of 30. This is going to be equal to 1/3, or we'll just say 0.332, 0.333, whatever. So what we'll look at, let's just look first on this first one, only looking at soil, this top layer. So the top layer here. So this is a mixed soil, so that means we need to have that negative contribution due to the cohesion, and since it is active. Also remember though that everything is going to be transferred down vertically, and then everything that has a vertical stress needs to be applied by this Ka1. So if we're talking about the, let's say, at different points, yeah, so let's just take Z coming this down here, this direction. So at Z equals 0. So what is, if we were hanging out right here, the only thing we would have would be that surcharge, this Q. But that vertical surcharge would need to be multiplied by, hold on, yeah. So let's look at the horizontal stress. So we would have that vertical surcharge times the Ka value, since this is horizontal stress. And then at this top here, we have the start of the cohesion. So we would have this, well, I'll write it in here, I guess. So the equation, the general equation would be this plus then Ka unit weight times Z minus 2C times Ka1. So since we're at that surface, though, that Z is going to be equal to 0. So this is going away. So here we would just have Q times the QA minus 2 friction angle times the Ka. So this would equal 800 PSF times Ka, which was 0.332, and minus 2 times the cohesion, which was 600 pounds per square foot, and then times the square root of 0.332. And so as we'd expect, this would be negative, even with the surcharge, negative 426.18, 4.15. So if we were actually drawing this profile, then right here at this very top of soil A, so still within soil A, but very top of it, then we would have a negative 426.115. So it would be on the other side of the equation. So this brings up a second point where a lot of times also this surcharge might be applied to offset that negative amount. So this was a offset. We have a surcharge of 800 pounds per square foot. But we still have this negative section here, 426.15. So in some cases, they may try to increase that surcharge by either increasing the density or applying concrete or some type of tension things to increase that surcharge to offset for this 426, so you don't have that negative tension if the construction considerations weren't there. This is all H. Okay, so still looking at soil A, let's look now at the depth Z equal to 10 feet. So right here. Now what we'll see though is that we are still in soil A at 10 feet. So we'll still be right here at soil A and 10 feet. So we still have our soil A properties that we're going to be working with. So the equation, the general equation will be same as before, where we have this coefficient of our surcharge being transferred all the way down. But now we have the total stress being considered, and then the portion here still being applied. So I'm just going to remove the units here just to make it go a little bit faster, but two times the unit weight of 110 pounds per cubic foot, and then times 10 feet, so we're still in pounds per square foot. And then we're subtracting out this cohesion, 600 times the square root of 0.332. So this is at Z of 10 feet. And then if we do that out, it's equal to negative 54 or something. Or 59, 48, right. Yeah, pounds per square foot. So this is Z equals 10 feet. So, but this is still soil A because we are still using soil A properties right here, right here, right here. We're still using soil A properties. So we could say like this is like 9.99999 feet. You know, we're still in that soil A region. But as soon as we go past this next layer into soil B, then we have different soil properties. We have a different Ka value since we have a different friction, and we don't have cohesion. So for soil B, let's find this bottom layer here. So we're still looking at active conditions. Now we're going to be in soil layer 2. So we still have the same thing where we have 1 minus, but now this friction angle is 35 degrees. And then 1 plus sine 35 degrees. Well, I'm noticing already, I think this was a typo. Yeah, so this should say saturated because we have a groundwater table there. So since we have that, we'll just assume that's a saturated strength. The only way we would be able to calculate the saturated unit weight is if we were given a moisture content. So remember this whole thing, gamma dry times 1 plus, you would use that equation if we had a moisture content in this case. But so we'll just assume that was a typo on my end and it should be saturated. So what we'll do though is we will look now in soil B, except same thing, Z going here in this direction. But now that Z is going to be right in the initial part of soil B. So at Z equals 10 feet still, but this is in soil B. So we're going to have different properties here. So our horizontal earth pressure, we still have our surcharge that is acting laterally, but now we have a different coefficient. And we have the depth consideration with total stress. Sorry. Should be times Z. And if we wanted to add the zero, the at least the function here of the -2C, we could, but there is cohesion equal to 0. So we know that this whole thing here, 2C square root of KA2, that this will all go out to 0 since there is no cohesion there. So our equation's a little bit simpler here with this. Now, the thing to note with this though is since we have the groundwater table, remember all of this analysis, all these K values, this is for effective stress only. All right, effective stress. So this means if below the groundwater table, then what we use is a gamma submerged. So gamma submerged is just the unit weight of the water, of the soil, minus the unit weight of water. And essentially that's a shortcut in calculating the effective stress in these cases where you're below the groundwater table. So in this case, the unit weight is going to be a unit weight prime or submerged unit weight. It's also sometimes shown gamma sub. So that would be 118 minus 62.4 pounds per cubic foot. And that would equal, I don't have the value, but you could do that math. What is it? What is a calculator real quick? $55.6. Also, sorry guys, I still can't breathe for some reason, so this has been fun. Every time I eat cereal, it's like I'm getting waterboarded. That's fun. But yeah, so this is our submerged unit weight, which is equal, sometimes shown as the effective unit weight. So this essentially allows us to show everything in effective stress terms, which is important because we got this little guy here, this effective horizontal stress there. So what we could do now is just plug this in. And this is at Z equals 10, but soil B. So that surcharge is still 800, but now we have, oh, I guess I never did that math out. So that's 0.271. Now we have 271. 1.271 times 55.6, which is the value there for the submerged unit weight. And then the Z, or the Z there. This is going to be 10 feet. since we have the 10 feet of soil above it. This is going to be 514.9 pounds per cubic foot, or pounds per square foot. So this is still soil B, just right at this is still Z equals 10 feet, but in soil B now. So if we remember from the last slide here, we were at negative in soil A. So when we're drawing this is going to have a discontinuity in our profile. We're going to have negative values and then it's going to shoot up. And we know this is just a graphical representation of the stress. We know that these soil stratigraphy is not a clear-cut straight line like this. But when we are estimating the resulting the resulting force being applied by the soil, we will still use that accordingly and divide it up into triangles, which we'll show here at the end. So what we'll do now is at the very end here, so Z equals 30 feet, because we had 10 feet here and we have 20 feet here. So Z equals 10 feet. So I'm just going to plug them in here. 0.71 times 800 plus, well, yeah. Remember though, this is all still total stress. So if we're hanging out down here, we feel the surcharge, we feel the contribution from soil A, and then we also feel this contribution from soil B here. So we feel all of these added together. So we would have the surcharge, we would have KA, sorry. Oh, don't do it. Sorry, I don't know why that was. Yeah, so this would be from the soil A layer, then this would be the soil B layer. Yeah, this would be 816.25. So we would have all these key points now, because what we're going to be doing is creating the profile of that. We have this point of discontinuity here. So what this point would actually look like then, the stress profile, if we wanted this to be so pounds per square foot. We know at this top we are at negative 426.15. And we go, this is not trying to scale at all, but whatever, 59.5. And then here at that transition, and we go to the positive of 314.9, and then down to 816.25. And this is at the depth of 30 feet. This is our active stress here. We just kind of like back with like, cross sections of beams and everything. This all is technically a tension. And then this would be the active stress that would be applying here. So you would have to divide these up to find that resultant. So we know this is our max stress down here, and this is our effective. We could also find the pore water pressure. Which we know is just starting here and going down like this. This would be 1248, which is just the unit weight of water times, I guess, 20 feet. So actually what might be important is that max Rankine but in terms of total stress, which would be, remember, total stress is equal to plus our pore water pressure. So we could actually add this back in to find the total max stress instead. This would be Z equals 30. And you can find this, yeah, what would that be then? 20, 64.25. Huh. Okay. Not sure. Maybe I deleted it. Do you guys have a 4 out of 4 on your slides or no? Okay. Well, sorry. So what you would do, I'll just try to write it in a different color here on the corner. What we would do normally is like for the active section, like active force per unit wall. This is technically the active section here, like actually active, right? This is actually more treated like a passive section because the soil is in tension. The wall is not actually, or the soil is not pushing on the wall. Rather, the soil is pushing on itself, being a passive condition. So if we need to find the active force per unit wall, what we usually do would only look at this bottom portion that is positive, not negative. So to find this active force per unit wall, we would normally look at the positive section only, that being this whole thing here. So it's a trapezoid, so the easiest thing would be to divide this into the P1 and P2. So P1 and then P2. Here, I'll try to just do this right here. So our actual total active stress is going to be that P1, which is going to be 314.9. This is pounds per square foot. And then the area of that would be the depth, which is times 20 feet. And then plus that P2, which is that triangle. So that is going to be 1/2 times the base, which is 20 feet, and then times that height, which is 816 minus 315. Yeah, 314. Sorry, I'm running out of room here. So this would be the resultant active that you could then do the math out, and I did not do that math out in my notes, but that would be the resultant force. If it asked for the resultant total force, then you would also have to add that water from the pore water pressure. Now, most of the time in retaining structures, what you'll see is in the actual construction of these, you might see them every once in a while in real life too, but you'll see like these little like ports right here. And these would be to add, they're called weep holes. And the whole thing is the groundwater table behind a retaining structure is not a good idea because it adds a lot of force. That pore water pressure, that force of water, 120 or 1,248 pounds per square foot. That's a significant amount of pressure due only to the water. And that water can change. Also, we have issues with liquefaction and other change of properties. So most of the time, the goal would be to remove that groundwater table, thus only having that effective condition anyways. So real world construction of retaining walls, you'll almost always see these little holes on the bottom or some type of drainage like aggregate with a French drain right here that moves the water away from behind it, or even like a sump pump sometimes behind these things if they anticipate very wet conditions. So although in the analysis sake, you might have to add the pore water pressure, just know in the real world, most of the time, the easier thing, instead of over designing the wall for pore water pressure, the easier thing would be to remove the pore water pressure altogether by ensuring that water doesn't build up behind it. Just write that here. Yeah.
In slide number 2, when you were doing C equal to 10 feet for soil B, is there a reason that you didn't account for soil A on top of that? Like it was just in terms of Ka2 instead of Ka1.
So right here, or
Yes.
Z equals 10. So the yeah, because in Z equals 30, we added this soil A here. So since we are acting in soil B, we're saying that the added that layer of soil A is technically acting in terms of soil B. So in this case down here, this whole layer is out of, or is already accounted for right here because we are at the bottom. So if we're talking about like layers of it and you're just adding each layer, for Z equals 10 for soil B, we're still in that layer. We're just accounting for that transition from soil A to B.
It seems like you want it just for soil B, but not.
Yeah. A way to like kind of think about this, like, so rough. This could be a crash and burn example here, but like imagine you're like holding a weight or something and like over your head, and you like then go in a swimming pool and like you like lower yourself down where the weight is still above the water. So in that case, like the pressure like on your legs from that layer, it's still above everything. but like the pressure on your hand, since your hand is underwater with like that weight, is different. That didn't work. Yeah, I guess. I know there's got to be. Sorry, once the Tylenol wears off, maybe I can think straight. but yeah, since you're still technically in that soil A layer, so you don't treat it separately because you're accounting for that thickness of it, that like little slice of soil A already there. Where down here, that soil A is already just hanging out up there with your Ka1 condition in your height 1. Yeah, I forgot, I did not post that extra long tedious example, so I will be sure to do that after this class, and that will hopefully illustrate it a little bit more detail. We shall see. But retaining structures, I really just want to go over it because you know there's other design analysis and other types of retaining structures, real world stuff, like you start talking about like anchor systems and you know not like these gravity walls that we're talking about here. We're actually drawing these profiles are important because if you have a sheet pile, then the sheet pile could actually bend in a certain direction. So that's kind of stuff that would be on your PE if you decide to do a geotech PE. But for the FE, I'm almost certain they only just go over the general stress profiles and resultant forces, given the like the different either Coulomb or Rankine. So that's why I want to at least go over that. Okay, so what I do want to go over now is just a little bit of the exam. Which means